also like to thank the organizers for the invitation to speak at this workshop. I echo Jim that it's been a really great workshop so far, although I haven't been able to participate fully or as much as I'd like. So I'm going to, in the course of this talk, I'm going to try to highlight some of the big issues that I see, where things are going, some of the significant work in the past, and I'm also going to try and give some case studies from my own work that kind of highlight important issues that I see. And I would like to emphasize that this has been a big effort by many people, both in the groups that I've worked with and as well across the community. And for example, I wanted to highlight a couple junior researchers that have worked with me over the course of my studies here. So that Trevor Sprouse is currently a postdoc at Los Alamos doing nucleosynthesis work. Sanjana Curtis is a former graduate student, now postdoc at Amsterdam. Shomi Day was a former graduate student, I think, at no, not at RIT, but in New York, and now a postdoc at Los Alamos. And Kelsey Lund is a current graduate student visiting Los Alamos. But there's many, many more people. I just wanted to highlight the more junior people to start. So let's begin by just asking, when is neutrino transport relevant? Jim gave a really great discussion on why photon transport is relevant and where and when. But I just wanted to talk a little bit about when do neutrinos matter. And most of what I'm going to talk about is accretion disks also, but I wanted to highlight that there's a lot of places where neutrino transport matters, and there's several reasons. So one reason, obvious reason neutrino transport matters is in the energetics of core collapse supernovae. A supernova won't explode unless it's heated by neutrinos. It's the more common question people ask about neutrinos outside that community, I would say, and inside that community as well, is how it affects nucleosynthetic yields, because neutrino transport controls neutron richness, which powers our process nucleosynthesis. And so here's two sort of figures where this is kind of relevant. So the in-spiral merger of neutron stars and neutron star black hole systems. Neutrino transport is relevant both in the in-spiral and plunge, and also in the post-merger system, where you may have a hypermassive neutron star or a black hole with an accretion disk orbiting it. And for another place where accretion disks form is in the collapse of massive, rapidly rotating stars, where you might form where the core, if bounce fails and it doesn't explode, you may get a core which is a neutron star or a black hole with an accretion disk forming around it as the infalling stellar material circularizes. So just to give you a highlight of how neutrino transport matters, not just in the sense of, well, neutrinos are emitted, but really the multidimensional transport, I wanted to share with you a little thought experiment that you can do with the simulation. Where what I've done here is I've taken a gas, put it in sort of accretion disk, post-merger accretion disk temperatures and densities, and electron fraction. So this is like a YE of 0.2 or something, electron fraction being the ratio of electrons to baryons. So low electron fraction means more neutron rich, higher electron fraction means less. And then I just put one region here with a little bit more higher electron fraction, one region with a little bit lower. And then I put membranes around those regions. So the gas can't mix, but neutrinos can go through the membranes, you let them go, and they carry left conserved electron number from one place in the domain to another, which changes the electron fraction and brings the whole system, in this case, to equilibrium. And you'll notice that the electron fraction of the gas at the end of the simulation, after things have come to equilibrium, is actually different than the average electron fraction at the beginning. And this is because conserved electron number is being carried by the radiation field. So the equilibrium state, there's actually electron number not in the gas at all. So Jim talked about this in great detail, but I want to add a little bit of sort of what the limits of sort of the full transport equation are, and talk about when you can get away with what. So to do this, I'll characterize things by optical depth, which is basically this decay constant in front of the radiation intensity field. And I want to note that there's also an effective sort of scattering optical depth that I'm going to conflate with the absorption optical depth. For the purposes of the discussion here, it's not going to really matter which is which, but it's, of course, the physical processes are different. If you're scattering, that is different than if you're absorbing. So In the very, very low optical depth limit, neutrinos are essentially free streaming, and you can basically treat them as an energy sink or a lepton number sink. So for example, our sun, the core of our sun is emitting neutrinos, and for most of the body of our sun, it's completely opaque. It's completely transparent to neutrinos. On the other hand, at the very high optical depth limit, neutrinos are essentially trapped, and as Jim discussed, they diffuse through the system. And so a good example of this is a hot, dense nuclear matter, such as a protoneutron star at a core collapse supernova, or a hypermassive neutron star after a neutron star merger. And somewhere in the middle, the optical depth is not in one of these limits, and then you want to solve the full Boltzmann equation if you can. And there's, again, Jim talked about this in great detail, so I'm only going to briefly discuss this, but there's a bunch of different ways that you can do this. I'd classify these sort of into two categories: approximate and full, maybe three categories really: approximate solvers, full solvers, and sort of hybrid methods. So the full solvers also break into essentially two categories that Jim discussed. There's the mesh-based methods, which I think Jim called ray transport. And these fall into a couple, they're all basically that flavor, but they fall into a couple different categories, I would say. There's discrete ordinate, which are basically how you discretize the grid. So there's discrete ordinates methods where it's kind of a finite differences method in momentum space. There's sparse grids methods, which are really a grid, so less than a discretization. And there's spectral methods, for example, where you put your momentum space in where you project it onto a basis set. And there are also mesh-free methods such as Monte Carlo, which I'm going to talk about in more detail. Approximate methods, Jim discussed quite a few: leakage, moment schemes. I would also like to add that there's diffusion. I'd like to add leakage and cooling functions as these extra methods that people often use in the community. So cooling functions, of course, are the free streaming limit where things just escape immediately. Leakage is somewhere in between, where you modify this cooling function by the amount of optical depth that radiation has to travel through to escape to infinity. And leakage schemes are very popular, and they can handle more ranges of optical depth than cooling functions, but they're still not real transport. So if you really need to understand the multidimensional effects of, say, lepton number moving from one part of the domain to the other, they can't really capture that. And there's quite a few interactions between neutrinos and matter that are important to study. Here's a smorgasbord of them coming from Burroughs, Reddy, and Thompson this was, of course, mostly discussed in the context of core collapse supernova, but it seems to have translated fairly well to other contexts. And one thing I want to emphasize here is that a lot of these are only treated approximately. So for example, things like weak magnetism, often people don't treat that. And in neutrino fields, you can get something very interesting: stimulated absorption as opposed to stimulated emission for photons, where because neutrinos are fermionic, if the radiation field is degenerate, it preferentially wants to be absorbed. And so you can get this kind of inverse process compared to stimulated emission. And also neutrino annihilation is a very common thing people are interested in looking at, for example, for powering jets. But neutrino annihilation is very difficult to treat accurately unless you have access to the full distribution function. And of course, all of this is ignoring neutrino oscillations, which I would argue are the biggest bugbear, so to speak, in treating these issues. There's been some really promising work, for example, by Sherwood Richards and Mengru Wu, but there's also really no handle, I would say, on how badly we're doing. We really don't have this under control at all, and full simulations don't incorporate this at all. So going to zoom in on accretion disks in particular here, and we can try to ask, how much does transport matter? What can you get away with? When is it appropriate to use approximate techniques, and when is it not? And this plot that I've made here, I've tried to summarize the work over many, many years. I would say the earliest of the references that are relevant for this go all the way back to like the early 2000s or before. And just to highlight a few recent and significant contributors, I've listed a few in the bottom. Ramirez-Ruiz, Siegel, Radice, Just, and Perego, but this is definitely a non-comprehensive list of the people who have contributed. And so what I'm trying to plot here is on the y-axis, I'm using optical depth as kind of a proxy of importance of neutrino interactions. On the x-axis, is accretion rate, but accretion rate roughly correlates, at least for post-merger disks, to the mass of the disk. And so the top x-axis is the same as the bottom x-axis, but it's translated into sort of the mass of the accretion flow, of the total amount of mass that can be accreted. And so on the very bottom left here, we've got very low optical depths and low to, and this is neutrino optical depth, I should emphasize. For all of the scenarios that I'm going to be talking about, the photon optical depth is often enormous, like 10 to the 15 Eddington kind of accretion rates. The photons are essentially just part of the gas. So they're at the lowest optical depths, at some point there's no neutrinos, the gas is not degenerate, and I've listed this sort of as no ignition. And systems that you might think of for this are like super Eddington accretion flows that Jim talked about, like X-ray binaries and things like this. As you turn up your accretion rate, eventually you get to flows of about a percent of a solar mass per second or less. This can be relevant, for example, for collapsars or superluminous supernova. Turn it up a bit further, you get to neutron star mergers. Accretion rate, binary neutron star mergers can get accretion rates as high in the early couple hundred milliseconds, as high as about a solar mass per second, and accretion disks as large as 10% of a solar mass. And there's even this higher, more extreme regime where if you have a very highly spinning black hole that merges with a neutron star, if the merger parameters are just right, the neutron star can essentially completely tidally disrupt before it plunges into the ISCO. You can get an enormous accretion disk with masses like 40% of a solar mass accreting around this black hole, and accretion rates higher than a solar mass per second. This is somewhat speculative since, as we've observed so far, most of the black holes in the LIGO band have not been spinning very rapidly. Nevertheless, it's possible. And I want to highlight that I mentioned that the photon Eddington rate for, say, the neutron star merger case is like 10 to the 15. The neutrino, quote unquote, Eddington, these flows are going at about 10 to the minus 3 Eddington. And this extremely high mass ratio, I want to mention that you should keep an eye out for Sajana Curtis's work on this. She has a paper in preparation and should be quite interesting. Okay, so what do you need to do this disk modeling? Well, you need general relativity. For example, in the simplest case of black hole, simplest, quote unquote, a fixed rotating black hole spacetime. By fixed, I mean prescribed, so not dynamically evolving. You need plasma physics, which is most often approximated by ideal MHD. You need nuclear physics, and the common way that this is done in the community is that you treat the gas as being, the hot gas as being in nuclear statistical equilibrium, and so you incorporate the nuclear physics in an equation of state. But then this doesn't work for the outflow. The outflow cools below nuclear statistical equilibrium, and then you must treat it out of equilibrium via a nuclear reaction network. And in core collapse supernovae, because the energetics are so important, this never works. You have to have an inline nucleosynthesis network to get the right answer. And then on the radiation physics side, as I mentioned, the material is completely opaque to photons. And so those are incorporated into the plasma physics, but it's not opaque to neutrinos. And just for proof by intimidation, I suppose, here is the full general relativistic formulation of all these equations: mass and momentum conservation, magnetic fields, lepton number conservation, which I labeled here as composition, and neutrino transport, which is the neutrino mass is most often just neglected. And so neutrinos are treated as if they're photons to some degree, and so they obey the transport equation. So our group has produced Nublight, which is one way of doing this, which treats all of these things via some sort of standard methods: magnetized gas via finite element method, neutrinos via Monte Carlo, and they're coupled via first order operator splitting. And if you're interested in, I should also mention that this is built on a long history of numerical methods and achievements. So all the way back to Harm in 2006, Giarmonti for the Monte Carlo transport, and most recently Blight by Ben Ryan in 2015. So if you're interested in trying this out, it's open source. It's on GitHub. Here's the phone number, so to speak. And at this point, I'm going to transition into those case studies I mentioned. So to start, let's look at our best approximation of the first few hundred milliseconds after the merger in 2017, under one very strong assumption, which is probably not true, which is that the central object collapsed to a black hole rather promptly. So let's take a look. The top row here is zoomed in. The bottom row is zoomed out. The left column is a poloidal slice. The right column is an equatorial slice. The color is YE. So more orange is more symmetric. More purple is more neutron rich. And as you see at the beginning, you have this compact torus around the black hole, but magnetorotational turbulence very quickly disrupts that torus and drives angular momentum transport. And so you get this beautiful accretion disk. And that disk drives a wind in this hourglass shape that you can see in the bottom that goes outward. You'll notice that the hourglass shape has kind of a hole tunneled through it near the poles. That is the ultra-relativistic jet that's being powered by the accretion. And one other thing I want to highlight here is that you get this very interesting angular structure in the electron fraction, where the equator is lower electron fraction, more neutron rich. And as you move to higher latitudes, that becomes less and less true. And this angular structure is very much related to the weak physics. As Daniel Siegel and Brian Metzger argued, in large part, this is due to what the system prefers to be in and the degeneracy of the electrons, but it also has to do with neutrino transport, since the way that electrons transform into neutrons, for example, is via weak processes. And so here, what I wanted to show you is a very complicated way of trying to look at that. So on the left, I'm plotting the emission minus absorption rate. This is at very early times, again, up to about 100 milliseconds of electron neutrinos. And on the right, the emission minus absorption rate, the difference between the emission and absorption rates of electron antineutrinos. Ignore the cinch thing. Basically, all it is a signed log. And the point of that is that if you have, on the left, if you have a red color bar, that means emission is dominating. If you have blue, that means absorption is dominating. And on the right, purple means emission is dominating, and orange means absorption is dominating. And I chose those colors so that reddier means that the processes are driving electron fraction down, and bluier means it's going up. And you'll notice that at the very early times, things are mostly dominated by the emission and absorption of electron neutrinos, where electron neutrinos are emitted at the equator and absorbed at higher latitudes in the corona. And this is what sets, at least at very early times, what the electron fraction is and creates this angular structure. At late times, things are different. It's basically just a balance between the emission processes for electron neutrinos and anti-electron neutrinos. And that tension is what sets the electron fraction at late times. So if the angular structure actually translates into the outflow, which translates into the nucleosynthetic yields, and that translates into electromagnetic observables like a kilonova. I want to emphasize that this story changes as you vary the accretion rate. This angular structure that I talked about, that does seem to be does seem to be generic, and it's seen by most groups. But the details, what those electron fractions are, whether or not you get a third peak, et cetera, this changes very much with accretion rate. And I wanted to point out again, Sanjana Curtis is going to be looking at the very high accretion rates in the near future. And I also wanted to highlight the work of Shomi Day in collaboration with Daniel Siegel, where they looked at very low accretion rates, and they looked at how when you vary the accretion rate at below about 1% of a solar mass, how things change. So I wanted to dig in a little deeper into this question of how that angular structure forms and what it looks like. And to do that, I'm going to do another case study of a much lower accretion rate system, which is sort of a collapsar disk. And what I'm going to argue to you is that the story I'm going to tell makes sense regardless of whether or not absorption is important, because you can frame it in terms of timescales and questions about equilibrium. But the details of what this story means, of course, change with accretion rate. So the story begins with two facts. The first fact is that even at these low accretion rates, the electron fraction is not the same as the equilibrium electron fraction. The system is, to some degree, out of equilibrium, even when the disk is sort of in a quasi-stationary state. And that's shown on the top left here, where I'm plotting the expected equilibrium value of the electron fraction on the left panel, and the difference between the electron fraction and its equilibrium on the right for some snapshot of this collapsar simulation. On the bottom right panel, I'm showing the other fact, which is that this flow, although it looks kind of smooth in these snapshots, is of course very turbulent because it's driven by turbulence. And so what I'm plotting here are tracer paths, so little Lagrangian fluid packets affected by the flow. And as you just a few selected ones, and as you can see, their motion is very, very chaotic. They're essentially random walking through the disk. And that leads to this cartoon picture where there's this tension between the fluid motion and the weak processes. So you might imagine that you have some particle or some fluid element that's, say, in the middle of your disk, and it wants to move. For whatever reason, it's moving upward vertically in the disk, and it's random walking through the disk. And so there's some characteristic timescale given by that random walk that for how long it will take to rise to higher latitudes. As it rises, the equilibrium value of the electron fraction, the value it wants to have for equilibrium, for weak equilibrium to hold, changes. It starts low at the equator, and it rises as the conditions drop. And neutrino processes, of course, want to drive you towards weak equilibrium. So this fluid element begins to rise. It interacts with neutrinos to try and drive it to equilibrium. And whether or not it achieves equilibrium depends on how quickly those neutrino processes can act compared to how quickly this fluid element is moving through the disk. And you can actually look at this in a model if you have access to these processes. So this is another, again, apologize for the complicated plot, another complicated plot trying to get a look at this. So on the left panel, I'm showing the ratio of weak processes that want to increase the electron fraction versus weak processes that want to decrease it. So white means that you're in weak equilibrium. Purple means that you want to raise your electron fraction, and green means you want to lower it. On the right panel, I'm showing the ratio of those processes, those timescales, to the timescale of this turbulent kinetic motion. And so if the turbulent kinetic motion is dominant, then it's more red. If the weak processes are more dominant, then it's more blue, meaning weak processes happen very quickly compared to the fluid motion, where if it's red, they happen very slowly. And far away from the accretion disk, of course, weak processes are essentially frozen out. Things happen very slowly. You're very far from weak equilibrium. If you're very blue, then weak processes happen much more quickly than the fluid motion. And so you're able to achieve weak equilibrium. And somewhere in the middle, white and orange, then things are in competition. And then the angular structure of the disk is really set by this tension between the turbulent motion and the weak processes trying to drive you to equilibrium. And you can actually work out with sort of a simple semi-analytic model, just basically a line, a linear fit. If you take a linear fit and you plug in your assumptions about the appropriate timescales and the appropriate rates, perhaps pulled from tracer data or perhaps pulled, then you can actually match that very nicely to the electron fraction as a function of latitude as measured in the disk, which is what I'm plotting on the right here. So the dashed line is the semi-analytic model, and the blue curve with error bars is what's actually measured in the simulation. And so this is a little bit circular since we took this picture from the simulation in the first place, but it shows that this cartoon picture really does meaningfully describe what's happening in the system. So that's all to say with these two, that the relevant pieces of this story are really about these timescales and about capturing the relevant processes that matter, which is both the fluid motion and the appropriate neutrino interactions. And which interactions matter, whether absorption matters, whether scattering matters, this really depends on the problem. But there are certainly problems in this space where everything matters, especially at early times where the accretion rates are quite high. Of course, this is all I've described so far is about accretion disks, but this is not all we want to study, of course. For example, in spiral, of course, you have neutron stars, and post-merger in a binary merger system, you may end up with a hypermassive neutron star. In supernovae and superluminous supernovae, for example, collapsed stars, you may end up with a magnetar at the center as opposed to a black hole. And then you need very large optical depths. And in fact, you need to span all optical depths because the disk around your neutron star is going to be low optical depth. Your neutron star is going to be high optical depth. So this is a problem for Monte Carlo because Monte Carlo can be very challenging for large optical depths for basically the reasons that Jim described, which is that it's hard to tamp down the noise in systems where, for example, scattering is very dominant or the radiation pressure is very high. And also the method gets very expensive because if a particle is just scattering around, it never moves. So there are a couple options to get around this, and I wanted to highlight sort of hybrid methods in particular. So for example, Francois Foucard has a moment scheme that's coupled to Monte Carlo, and he has also developed an implicit moment scheme, or an implicit Monte Carlo scheme, both of which get around some of these issues. There's also, of course, methods that are just directly solving the Boltzmann in full power, such as the discrete ordinates methods that Jim described, and also spectral methods, which are in similar flavor. And then I also, of course, wanted to highlight MockMC, which is the method, Jim mentioned it briefly. It's a hybrid method where you close a moment scheme by a long characteristics method, where you evolve particles through your grid, and then those particles inform your Eddington tensor. And so you are solving the full transport equation, but you're freed from having to allow your moment from forcing your particles to do conservative things, and you can allow all the conservation to happen in your moment scheme. And on top of that, you can turn off your particles if they're no longer appropriate for the transport. So just to conclude, we need GRMHD and neutrino transport to model these systems. I don't think I need it to convince anyone here that neutron star mergers are a likely source of heavy elements in the universe. And there's a large diversity in the outflows and the physics that can happen here. And whether or not you need to use sort of the full neutrino transport I described, that really depends on the problem you're trying to solve. But very generically, the really important thing is the competition between the fluid physics and the neutrino physics. That's about all I had to say. Thanks.
Okay, thanks so much, Jonah. Any questions? Let me see if I can see some hands, some clapping. Clapping looks a lot like hands. I guess that's because you do it with your hands. Oh, I had a question and it fell out of my brain. Anyone else? Zvi, yes.
Hi, very nice talk. Thank you. Yesterday in the discussion, the question of neutrino electron and anti-electrons annihilation as a source of energy for powering jets was raised. Can you calculation of accretion disks around in neutron star mergers shed some new light on this question?
Yeah, this is great. So in principle, yes. Currently, no. So the model that we used for the simulations that I showed here, we had a very approximate treatment of annihilation, where we essentially used rates that weren't really informed by as well as they could have been on the distribution function. So the way to do this is if you have access to the full distribution function, you can actually just measure what the annihilation rate should be at any given place. And then you can measure how much energy is injected. And Francois Foucault actually did this in post-processing. There've been a couple, he's not the only one. I believe Sherwood Richards has as well. But done dynamically, this hasn't been done yet. And this is something I'm very interested in doing. So if you're interested in collaborating on this, let me know. There are techniques to do it for Monte Carlo. For example, Wong et al. Did a similar approach for sort of 2 photon effects in accretion disks. So it's quite possible to do.
One more question, Agnieszka.
Hi. It's interesting that you have this collapsar model. I want to ask about some more details. How do you model this collapsar scenario? I mean, how it differs from the post-merger torus around the black hole that is used for binary neutron star mergers? Do you have some collapsing star around this torus, or how is it coupled to the star?
Yeah, no, I think at the level of modeling the long timescales, I would say your simulations are the state of the art. What we're doing is much simpler. So all we do is we set up an accretion disk with the appropriate accretion rate around a black hole with sort of the right mass and spin. And this is sort of motivated by this argument that was made by Siegel, Metzger, and Barnes, where they showed that you can kind of map for a very short amount of time a disk with a given accretion rate based on the fallback history of the collapsar. So this is just like a tiny snapshot of the full history of the collapsar. It's not the full thing. And I think there are issues with this kind of story where you don't actually forget your initial conditions like you might hope you do. So what we really need to do is we need to feed this thing with an infalling circularizing envelope like you're arguing for. I think that's really what we have to do to make progress.
Okay, thank you very much. Great.
All right, thank you, Jonah. Our next speaker is Enrico Ramirez Ruiz, and